In this video, we'll solve example 12.2 from Solution Techniques for Elementary Partial Differential Equations, second edition by Christian Constanda. And we're using the method of characteristics. Now remember, with the method of characteristics, you're thinking about the problem from the perspective of some moving observation point. Now, for this differential equation, our u depends on a position x and time t. So in this case, with method of characteristics, you're thinking of x as a function of t. So let's say here I am on the x-axis and my position is described by x as a function of time. Well, the velocity or my velocity would be described by x prime of t. And keeping that in mind, we'll be able to solve this differential equation. After we solve the differential equation, we're going to want to visualize it from a couple of different perspectives. And there was one more thing I wanted to do, but I can't remember what it was. So maybe if I think of it, we'll do it. And if not, that's okay too. All right, so we've got this. And we're going to let u be a function of x and t. And we'll assume that x is a function of t. Again, x is the location of our moving observation point. And we want to know what u is from the perspective of someone at this location x. I guess I should specify that that's at that location at time t. Well, when I take the total derivative of u with respect to time, and I'm replacing x with x of t, if I do that, I have to use the chain rule because u depended on two independent variables initially, and then we're saying that that first independent variable is actually dependent on the second one. Anyway, the total derivative of u with respect to time is the partial derivative of u with respect to x times the derivative of the inside with respect to time, so that's dx dt, plus the partial derivative of u with respect to our second variable, which is time. Now, each of these terms has a meaning. This is the change in u with respect to x. Or excuse me, with respect to t as x changes. So that's the change in u with respect to t due to our movement along the x-axis. And then this term is the change in u at a fixed point x. So maybe there's someone that's not moving back and forth on the x-axis, they're just standing there. This is the change in u that that person would see. This is the change in u that comes from the fact that you're moving back and forth on the x-axis. Well, if we compare this expression here to the left-hand side of the differential equation, we have this. The partial derivative of u with respect to x can be represented that way in subscript notation. And then we're multiplying by 3t. And then we're adding the partial derivative of u with respect to t. Just through pattern matching again, the coefficient of the partial derivative of u with respect to t, or excuse me, with respect to x, is giving us our x prime. So it's giving us our velocity. So in this particular case, our x prime is equal to 3t. And I would write that down over here. And I can take that and solve for x by anti-differentiating. So we end up with 3/2 of t squared plus some constant. And if we say that at time t equals 0, x is equal to x naught, then that constant has to be x naught. Now, these are the equations, excuse me, of our characteristics. And if we want to, we can graph them in the xt plane. So when x naught equals 0, we've got x equals this constant times t squared. It's basically a parabola. And there's another part of the parabola over here. It would be symmetric, but we don't see it. As this x naught increases, we're crossing the x-axis at larger values. So we're just going to see like different parts of our parabola. Now x naught can also be negative because remember x can go from negative infinity to infinity. So we're just going to see those parts of a parabola right here. These are the characteristics. If you want, you can keep graphing them. They're just parabolas on their sides, and we're only looking at the top half. Okay. Now, du dt is also equal to the right-hand side of that differential equation, which in this case is 0, same as in the last example. So we're on the characteristic. So we're traveling along this path with a velocity of 3t, velocity given by 3t. And we know that du dt equals 0 there. And that means that u of x and t is equal to some constant. And I know it's a little weird that constant might depend on x or t, but it's constant as long as we're on the characteristic. So we want to find the value of that constant. So usually we would get that constant by itself. In this case, it's really easy because it's already by itself. And then we say, well, what does that function have to be? Well, we know that at any x value and t equals 0, our u is equal to a cosine function. So at x naught and 0, and again, that's where our characteristics pass through the x-axis, we know that u is equal to cosine of x naught. So looking at this, you can see it's really a constant. No matter x naught is always constant, or this function will always be constant on that curve, and that constant value is equal to cosine of x naught. Now, in general, we can write this in terms of x and t by solving this equation for x naught. So I've got x naught is equal to x minus 3/2 t squared. So our constant function is cosine of x minus 3/2 t squared. And in this case, it happens to be equal to u of x and t. Okay, so we started with this cosine graph, and it looks like this. If we want to, we can change it up a bit. Let's look at the interval from 3 pi to 3, or negative 3 pi to 3 pi. Okay, so we've got that. Now, if we want to, we can graph the solution. And that was that function cosine of x evaluated at x minus 3 over 2 times t squared. And we can see how that changes as t increases. I want you to notice that cosine graph is actually moving to the left part of the time and then the right the other part of the time. And that's because our velocity was 3t. So we're going to move to the left when t is negative, and then we're going to move to the right when t is positive. So it kind of looks like this cosine graph is bouncing back and forth. Now, I actually made a mistake when I wrote the problem statement down, but that's fine. So this wasn't actually example 12.2. It's a modified version of example 12.2, where the right-hand side is 0. But we could just as easily have something that's non-zero on the right-hand side. So let's say our PDE looks almost exactly the same. But instead of having a 0 on the right-hand side, we have the function u itself. And we're still interested in this for all real numbers x and for times greater than 0. And keeping that in mind, actually, it would never go to it wouldn't bounce back and forth. The graph that we were looking at was showing for positive and negative values of t. So maybe I should change that on the Desmos graph. But we still have u of x and 0 equals cosine of x for all real numbers. So we've started with a cosine graph. And we know that du dt is equal to the partial derivative of u with respect to t plus 3t times the partial derivative of u with respect to x. And that's equal to u. So we had x prime of t equals the coefficient of the partial derivative of u with respect to x, which is 3t, which implied that x of t was equal to 3/2 t squared plus x naught. And those are the equations of the characteristics. So we're still on these parabolas here. But now, instead of having du dt equals 0, our right-hand side is u. So when we're on the characteristic, du dt is equal to u. And this one's actually really easy to solve. You could solve it by separating the variables if you want to. But you can also just think about this, like what function can you take the derivative of with respect to t and get the function back? Well, it's obviously an exponential function. So u of x and t is some constant times that exponential function with respect to time. So we're going to have an e to the t. But notice that I've written this constant as a function of x and t. I know you're probably thinking, well, it doesn't look like a constant if it's a function of x and t. And you're right, but it is constant when we're on a characteristic. So when we're on this path, we're going to get a constant here. Now, in order to find the value of that constant, we solve this equation for the constant. So we have c of x and t is equal to u of x and t divided by e to the t, or multiplied by e to the negative t, same thing. And then we're going to say when we're on, when we're on the characteristic, this is equal to a constant. So we can pick any point on the characteristic and plug that in, and that's going to give us the value of the constant on the characteristic. We always choose the x equals x naught, t equals 0, if that's what's given to us in the initial condition. And in this particular case, it is. We know what u is when x equals x and t equals 0. It's always equal to cosine of x. So at x naught and 0, our constant is equal to u of x naught and 0 times e to the 0, which is, of course, 1. And so we get cosine of x naught. And now I've got cosine of x naught, where x naught in general is x minus 3/2 t squared. Now you might think, okay, isn't this exactly the same solution that we got over here? It's not, because this differential equation had a non-zero right-hand side, and we ended up with this constant times e to the t. So u is actually this function times the e to the t. And we can graph this and get a sense of what's going on the characteristic and then in general. Okay, so we're at desmos.com. And we are looking at the function u of x and 0 equals x naught. So it's just this cosine wave. It's a cosine curve. Now we're going to take that and we're going to evaluate it at x minus 3/2 t squared. And that's going to move the graph. It's going to move it to the right with a velocity of 3t when t is greater than 0. And it would move to the left of the velocity of 3t when t is negative. But we're supposed to assume that t is positive here. But then the amplitude of that wave is going to change. It's always going to be equal to this e to the t, like we found on the piece of paper over here. So let's look at u of x and t, or u of x as t changes. It's going to be this function. And we see that graph right there. I think it's pretty cool. It's cool looking. Now I've chosen to let t be negative, but the problem statement says we should only be interested in t positive. So I guess we could change this if we wanted to. We could start at 0. And then we would just see it growing. I think it's cool to think about t negative as well. Okay, so we've got that, but we could also graph this in 3D. So let's look at it in 3D. So I've got u of x and t, but I'm going to have to write u of x and y because of Desmos and how it graphs things. And we've got e to the t, or e to the y, times cosine of x minus 3/2 y squared. So there's our graph. It's kind of pretty. Now, if you look at it from the top, you can see those characteristics. It's where x is equal to 3/2 t squared, those parabolas that I was talking about. That's where our cosine function is going to be equal to a constant. Now, u is not equal to a constant because we end up multiplying by the e to the t, which in this case is represented by e to the y. But that is our graph. If you look at it this way, you can see u as a function of x almost. And if you look at it this way, you can see u as a function of t almost. And I think that's pretty cool.